Okay, so now we have to be careful. Michael, how are we going to do this? Michael, what is Despina's role in this? Michael, you have no microphone.
So welcome everybody.
Okay, good. Finally. Can I just check with you what
Yes.
Despina is going to be helping
Well,
us?
Despina is we'll meet Despina at the gate of Alice. So
What gate?
here,
The gate here. Okay.
right
Can
now.
you hear me?
Yes, we hear you, Despina.
Yeah.
Okay.
One moment, I'll just show you my
Just
backside
you can see me also.
the gate. And now, ladies and gentlemen, now I enter here. Bonjour. Est-ce que vous pourrez me peut-être
I take this
yeah,
and
and then you give it to me. Just
yes.
Look at me.
Like this.
At the
The other,
yes, like this. It's good.
how can I?
This is me. This is fine.
Yes.
So
Okay.
Just
Like this.
okay.
So this is the security guard on the gate to Alice, helping us. Okay. Now we assume that Michael has ridden all the way from the CERN main site, which is about 2 kilometers, 3
Yes,
kilometers.
sure. You're welcome.
Bye.
And he's just fought. No, he hasn't fallen off.
Camera is still fine. It's slippery because it's just rain. It's rainy. So there you can see we take full risk. So I enter here at CERN point 2.
This is the site of the Alice experiment. And on the wall there you see, let's say, an artist's impression of Alice. And that's what we're going to see underground. Here is not as deep as at CMS. But it's still quite a long way down.
So here I will park my bike right underneath of the mural of Alice, and this is in here underground you will see the Alice experiment. I want to explain. I will introduce to you my dear friend and colleague from the Alice experiment, physicist Despina, who will bring you down.
Hello.
Underground. Hello, Despina. Thanks
Hello,
for hosting us today. Well, and I would say I will go in and I'll change the pin your camera
Okay.
and your main broadcaster. And well, maybe we enter first in the
The control room. Okay.
So let's follow this pin.
Michael, we're still getting a lot of echo.
Yes, because we have two cameras close by, but I will close down mine in a second.
Okay.
Maybe I'll film you first.
Okay.
Can you mute your camera for a moment? So you're on your you're online. Maybe you can explain where we are right now?
So what are we using, your telephone or mine?
Maybe with yours. I mute mine.
Okay. Hopefully you can see me and hear me. So we are in the Alice Run Control Center, which is on the surface, and you can see around. Can you hear me?
Yes, we can hear you.
Yes.
It's okay.
Okay, thanks, Mick. And you can see lots of screens, a lot of stations, but no activity really, because the LHC is in shutdown still. It will only start again next year. So there is no data taking, therefore there are no people in here. Normally when we're taking data, there are at least 4 people changing every 8 hours. And often there are many more, all the experts of each system, since ALICE is an experiment consisting of 15 different detector systems. So if you want to have a look at the screens, which at the moment show in principle photographs from previous situations, since there is no data taking now. Here you see a screen with the names, photographs, and telephone numbers of the experts of each system. During normal data taking, we need to be able to contact the person on call from each system in case of problems. Here you see a screen from what is called the data quality monitor, because during data taking, somebody monitors continuously the data as they come from each individual detector. And if he or she detects a problem, they call the expert in order to fix it. Then you see a screen showing the detector control system. You see little boxes with acronyms of the different detectors and colors indicating the state of each detector. When we take data, all detectors should be green, ready. Right now, many are dead, as it says, because they are switched off or not connected or something, since we are still in upgrading our system. But during operation, during data taking, there is a person dedicated to the detector control system, because depending on what's happening with the LHC, it is necessary to change states of detectors. If a detector has a problem, we exclude it from the run and do something, and so on. Next to it is the event display, which is, we could say, a photograph of a collision. The data, which are in principle numbers recorded from the different detectors containing the information, are reconstructed, and they are shown here together with the geometry of the detector. You see the orange towers represent energy deposited in the calorimeters. If you can see the curved lines, they represent the trajectories of charged particles, which are curved due to the magnetic field. And as you see, it says live. This is indeed live when there is data taking. Now these are recorded collisions from the last run, which was back in 2018. Here you see a screen which indicates the different detectors and whether they are in the data taking or in the trigger and so on, plus rates from each of them. And maybe it's worth showing this, what we call page 1 of LHC, which during data taking informs us at any moment what is the situation with the collider. Now it says proton physics stable beams, so it corresponds to a situation where we were taking data. The plots show the intensity of the two beams, red and the blue, as a function of time, as well as the energy. This is the black curve. And also there are comments. The operators make announcements there about what's happening, what's going to happen, if there is a problem, when it will be solved, and so on.
Last week we have been in the
Ah, you visited, so you've seen all that. Okay. Okay. So maybe now it's time to go down and see the real experiment. Okay.
Okay, Despina, maybe while
Yes.
you and Michael are moving towards the access shaft, maybe
Yes.
I can say a few words about what's different between
Sure.
Alice and the other three
Okay.
experiments.
Very
Okay,
good.
so as we learned probably right at the beginning, but we've probably forgotten, ALICE stands for
You
a
will also want
large
to come down.
ion collider experiment. Why ion? Michael, we can hear you. Please mute, okay? Okay, so a large ion collider experiment, what does that mean? Well, large and experiment is easy. Collider we know. Ion means that actually this experiment is more interested in collisions of heavy ions, ION. And in this case, they are lead ions, not protons. So we don't take protons from the bottle of hydrogen, accelerate them, send them into the LHC and smash them together for this experiment. What we do is we take lead ions. Now, interesting question is, where do we get lead ions from? Well, lead ion means it's a nucleus of lead. How do you get it? Relatively simple. You can take a pellet of lead, you can sit it in your hand actually, and you heat it up and the lead vaporizes. If you pass that vapor through a metal grid, then electrons get stripped from the lead atom. And then the lead atom becomes charged, and you keep doing this until you get to 82 plus. So the lead ions that they use here are 82 plus lead ions. Now, of course, as soon as you get a charged nucleus, as soon as you get a charged particle, then you can start playing all the games that we've played in the other experiments. We can accelerate them using electric fields. We can deviate them using magnetic fields. So the lead ions almost follow the same path as the protons. The beginning is not the same, but at some point they follow the same path from the proton synchrotron into the superproton synchrotron and then into the LHC. And they arrange to smash together at the ALICE experiment, which you can see on the top left-hand corner. Now, are the other experiments interested in lead ion collisions? Well, not LHCb, but ATLAS and CMS do take some lead data. But at some point, the lead ion collisions become so productive in producing many, many particles, CMS and ATLAS have to stop, otherwise they will saturate their detector. Okay, now why do we want to smash lead ions together? Well, it goes back to the Big Bang. Big Bang, when the universe was created, rapid acceleration, and at that point in time The idea is that all the constituents of lead ions and protons, etc., the quarks and the gluons were free. They're not free today. And the idea is that they were maybe living in a plasma, in a soup. And this experiment is trying to understand this plasma and this quark gluon soup. So it's pushing back, right back to the Big Bang, and trying to recreate the conditions immediately after the Big Bang, when these elementary particles, quarks and gluons, were free in a plasma, in a soup. Okay. Now, when lead ions smash together, of course, they're much heavier, so they produce many particles, in fact. And I'm sure Despina will talk more about this. So many more particles we will get at CMS and Atlas. So they're going down now to level -1. They're 27, 28 meters below ground. I said that they will not go as far as CMS. Remember, CMS was about 90 meters below ground. Here, I think we are almost there, actually. So here, the LHC is only about 50 meters below ground. Why? The LHC is of course horizontal, but the surface isn't. So the surface is a bit closer to the LHC here. Okay, so I'm going to hand over now to Despina, I think, if she can hear me, and she can tell us where she's going. All right?
Yes, can you hear me?
Yes.
Yes, we hear you clearly.
Okay, so I'm now, as you've seen from the little screen in the lift, 52 meters below ground. And right now I'm in the area where there are all the installations for the cooling of the experiment. The experiment that you will see, which consists of many detectors, has on each detector the electronics which process the signals and read them out. So all this electronics has to be cooled, mainly with water, otherwise everything would get very hot. So here there are all these installations. You see a little bit from one of the doors of the big magnet, but you will see much better when I go up some flight of stairs, so that I'm in a sort of platform in front of the experiment. So now I'm going up. The experiment has 16 meters, has a height of 16 meters, width 16 meters, and length 26, and it weighs 10,000 tons. Dimension-wise, it is the second experiment after Atlas, which is the biggest. Weight-wise, it is the second after CMS, which is the heaviest because it has more iron.
In case there are any questions, don't hesitate to ask Despina if you want to see something more details, please.
Michael, don't forget to switch off your camera, because you take over the picture if you speak.
No, I pinned
Okay.
I pinned the camera. Should be in the recording.
No, I can only see you.
Okay, so right now I am under the shaft from where everything has come down. You see the, let's say, the bright points are the surface.
50 meters.
And here, yeah, well, where I'm here now, which is the platform in front of Alice, this is higher. This is, let's say, 40 meters.
Okay.
You see a big crane, this yellow thing. This has taken all big pieces that have come from the surface down and then moves them to install inside the Alice.
Despina,
So
maybe you can say something about the history of this experiment, because actually
sure, yes.
it was actually a big part of it was used back in the 1990s, wasn't it?
Exactly. So what you see here, this big red structure is a big magnet, a solenoidal magnet, which before, as Mick said, belonged to a different experiment. It belonged to the experiment L3, which was housed in this cavern and which was taking data from the previous collider, which was installed in the same tunnel where LHC is now. That was LEP, the Large Electron-Positron Collider, that provided electron-positron collisions from 1989 until the end of 2000. And the L3 experiment was studying these collisions. That was one of the 4 LEP experiments. When LEP finished, it was agreed that Alice would be happy to take over the magnet. So this kept the cost of Alice relatively lower with respect to the other experiments, since this magnet came from free. The other magnet that you will see when I go to the other side, which is a big dipole, that is new. Anyway, both magnets are conventional magnets. I say this because I guess we have heard that the magnets of the Large Hadron Collider are all superconducting. The same applies for the magnets of Atlas and CMS. Our magnets are conventional, water-cooled. They work at room temperature. And this one, the solenoid, they works with 30,000 ampere, which creates a magnetic field of half a Tesla in the axis of all these things. This field is of the order of 10,000 times higher than the magnetic field of the Earth. And all this red stuff is iron, which closes the magnetic field when it is on. You see that there are 2 huge doors. Each of them weighs 300 tons. Right now they are open because we're in phase of installation, commissioning, and so on. They will close sometime before we need to get ready to take data. The operation of opening and closing the door takes some hours or maybe a whole day, because it's done obviously very slowly. And now if you want to have a look at what is inside the magnet, you have to imagine that along the axis there is a beam pipe. I don't know if you can see it already. There are some people working next to it. Afterwards, I will go near there if they don't mind, so that you can see better. Anyway, around the beam pipe, there are detectors in cylindrical form, one around the other. And these detectors see the passage of charged particles so that we can reconstruct their trajectories. There are other detectors which identify particles, and then there are detectors which measure energy. So around the beam pipe, there are 7 now, because we have installed a new inner tracking system. There are 7 layers of silicon pixels. And then around them, there is a big gaseous detector, a big gaseous volume, which is called the time projection chamber. And during this, during the shutdown of LHC, we have upgraded it. We have changed the detectors which read the signal generated in this gaseous volume, so that its whole operation will be faster.
Despina,
yes.
while you're talking about the TPC, the time projection chamber, I know that Michael is not going to say anything, but I know that he was one of the key people that built this piece of equipment, actually the time projection chamber. And one day he invited me over, quite a long time ago now, and he took some remarkable photographs of me and him inside the time projection chamber. And maybe we can persuade him to put a couple of these photographs up on Google so that you can see what we're talking about. It's a all of this is remarkable engineering, but because you know him, I'll give him a plug. Okay.
Well, thank you.
Yeah, if there is time when I go afterwards, I can show. I have a presentation where there is a photograph of the field cage. I think this is from my collection of photographs.
Yeah, definitely. Actually, maybe I want to state here, thanks for the comment, Mick, because the Alice TPC field cage is the reason why I came back to the arts. Because when we constructed the Alice TPC field cage, which is a huge Coca-Cola can, 6 meter diameter, 6 meter long, and inside strip with aluminum strip. So it's like a kaleidoscope, and it's like magic to be in such a high precision instrument, which looks like an artwork itself. So, and from there on, I did not just take documentation, technical documentation photos, but also I started to have a look on this detector, on this technology with an artistic eye. So you are now in my birth science and arts venue.
Your arts birthplace, yes.
Yes. Well, not really the arts, but because I made arts already when I was in Vienna studying.
Sci-art.
The sci-art, yes, definitely.
Okay, thank you. Okay, Despina, keep going.
Okay, so if you want some more details about what it is that you are seeing, there is this big frame around the TPC. Okay, I mean, right now you don't see the TPC, you see various cables, supports, and things in front of it. Anyway, on this frame, there are 18 positions, let's say 18 holes in the trapezoidal form, and in each of them there are 2 super modules of 2 detectors which have the role of identifying particles. One of them is called the transition radiation detector, and it identifies electrons, and the other is called the time of flight. Maybe you can see some blue cables near the external sides of this frame. These are the signal cables from this time of flight. And this detector is called like this exactly because it measures the time it takes for particles to fly from the interaction point where they are created to the detection point with an accuracy of the order of 50, 60 picoseconds. This is really record time resolution, and with this time resolution, we can find very precisely the velocity of particles, and in this way identify them. Because particles having the same momentum, which we find from the curvature inside the magnetic field, go faster if they are lighter, they go slower if they are heavier.
Despina,
yes?
when I was talking, when you were on your way to have a look at
Yes.
Alice, I said obviously one big difference between Alice and the other experiments is that you are really focused on lead ion collisions. And I said lead ion, one of the characteristics of the lead ion collisions is that they produce many, many, many more particles than proton-proton collisions. So you have a super shower of particles that get produced in these interactions. How do you cope with this? How can you measure all of the properties of all of these particles?
The role of the silicon detector in the beginning and then of this big TPC is exactly to be able to see, in quotation marks, the traces from the charged particles produced from these collisions and separate them. Inside the TPC, the time projection chamber, charged particles, depending on how long a trajectory they do, they can give up to, I think, 140 points. Now, in very central lead collisions, here a parenthesis, lead ions are big compared to protons, so the geometry of the collision is not always the same. We can have central collisions when they come and collide really head on. or we can have less central and peripheral, where there is a small overlap between the two nuclei. Anyway, in the very central lead collisions, we have many thousands of particles produced from one collision. So you realize that if each particle gives 100 points inside the TPC, it becomes something really complex, very complex. But we have developed algorithms which can match correctly the point corresponding to each particle, and so draw each trajectory. Our purpose being exactly to be able to detect all particles produced from one collision. Then the other thing which is of particular interest for ALICE, and which makes it different from the other experiments, at least from the practical point of view, is that we want to be able to identify each particle, to know what type of particle it was. Therefore, we have a whole series of detector systems for this purpose, for particle identification. I mentioned two, the transition radiation detector and the time of flight. In reality, also the calorimeter, which is, well, here you just see the support, but anyway, as you see on the left, outside the support frame, there is an electromagnetic calorimeter. So this also identifies electrons, positrons, and photons. And by the way, the TPC also has the possibility to identify particles based on how much energy they deposit per unit length. And then I will go soon to the other side, where we have the mu spectrometer. That detector is dedicated to the detection and identification of muons, which are heavy electrons.
Despina, can I ask you? Yes. Can I ask you? For example, at CMS and Atlas,
yes.
They are also interested in identifying, measuring the properties of all the particles. But one of the things that they do there is that they make combinations,
yes.
looking for the particles that may have decayed into these particles, looking for Higgs boson, for example. So they do they look for patterns of particles, and then they put these particles together, and they're trying to identify if these particles came from something interesting. But with 1,000 tracks in your experiment, do you do this, or are you doing something different?
Sure. I mean, we do this also. This is the way you mentioned is another way of identifying particles from their decay products. This applies to particles which we do not see directly because they are short-lived, but we see them from the decay product. And for this, we need to be able to see and identify the decay product. And also we need to be able to find exactly where they come from, the vertex, their point of origin. And for the case of particles, for instance, which are not very, very short-lived, but they have a lifetime, so that they travel a little bit, let's say some millimeters or some centimeters from the interaction point and then decay. We need to be able to find with precision exactly this point. And one of the reasons that we have changed our inner tracking system and now have a new one, more precise, and also which is going near the beam pipe. We have a smaller diameter beam pipe now for round 3. This is exactly to be able to find secondary vertices nearer the interaction point. And in this way, I identify particles which are shorter lived with respect to, let's say, our possibilities during run 1 and 2. I hope I've answered your question.
Well, I was thinking more about. I was thinking about quark gluon plasmas and soups and things like this, which CMS and Atlas are not really studying. And this is one of the unique things that you actually do. So, could you say a few words about that? Because this is why you use lead ions, and you are different.
Yes, we use lead ions because we want to have the highest possible energy and also as much mass, if you like, at our disposal as possible. The energy is 82 times the energy of the proton beams, the total energy of the lead nuclei. So what happens when they collide is that as they travel almost with the speed of light, at the point of collision, we have a temperature and a density which are comparable to what existed in the very early universe. So under these conditions, which are similar to the ones of the early universe, the protons and neutrons of the lead nuclei, we can say that they melt and their constituents become free for a moment. Their constituents are quarks, 3 quarks for each, and also the gluons that keep them together. In addition, of course, from transformation of energy to mass, E equal mc squared, we have the production of new pairs of quarks, anti-quarks. And so all these, for a very short, very brief moment, exist in a deconfined state, quark-gluon plasma, which is, as Mick said earlier, the state of all matter in the universe in its very early age. In the case of the universe, we believe that something like a microsecond after the Big Bang, the matter was in this state, and then as the universe was expanding, which means that it was becoming less dense and less hot, the quarks and gluons became permanently imprisoned inside the protons and neutrons. What we do is that we recreate tiny droplets of this primordial matter, this quark-gluon plasma, in order to study its properties and to understand how the transition happens, because what happens is a transition, if you like, similar to transitions happening in water when it changes from the gaseous to the liquid or to the solid state according to the temperature and pressure. Here, in the experiment, after the time of the order of 10 to the minus 23 seconds, a transition happens and the deconfined state becomes hadrons. So we don't have free quarks and gluons any longer, but they form hadrons, which means particles made of quarks, and this is what we see. I mean, we don't see the actual quark-gluon plasma since it is so short-lived. We see the product after its transformation. But from what we see, and mainly by comparing what we see in the case of lead collisions and what we see in the case of proton collisions, where we don't expect the formation of such a state. So by this comparison and by seeing differences, we deduce that indeed this quark-gluon plasma is created, and we make various observations for its behavior, its characteristics. For instance, one thing that was actually announced before LHC had started by the experiment at RHIC, which is the relativistic heavy ion collider at Brookhaven, where they collide the gold nuclei. Gold is also a heavy element. There they had observed that this quark-gluon plasma behaved like a perfect liquid. And when this was first announced, it came as a surprise because one would have expected that the behavior of a plasma would be that of a gas. But LHC also confirmed this observation, that indeed it behaves like a perfect liquid and that there is a correlated motion of its constituents. And this is seen mainly in peripheral collisions. This is just an example of one of the things that we see. Other things, for instance, we measure the initial temperature of the state created from the lead collisions. And one way of measuring it is by measuring the energy, the spectrum of the photons emitted as it cools down. In parentheses, the photons do not interact with the plasma, so they do not get absorbed, so they come out. We measure them, but then by comparing with models and so on, we find that the initial temperature is of the order of 5 trillion degrees, which is some hundreds of thousands of times higher than the temperature of the sun.
Spinner, are there any
Yes.
plans to use different nuclei for colliding?
I think there is a discussion of doing an oxygen run. Oxygen is relatively light, but it will certainly give, if you like, an intermediate point. In the past also, I mean, LHC is not the first time that CERN is involved in heavy ion studies. Before LHC, in the times of when there was only SPS, the superproton synchrotron, there was a heavy ion run with lead beams colliding on lead targets. But before that, there had been runs with lighter elements. So obviously, they also offer some insight into what's happening.
Okay,
And
maybe
the
you
other
can.
thing that I should mention is that there was some years ago during run 2, there was a run with the xenon beams. So that also gave an intermediate point and I mean, produced interesting results. Anyway, what were you saying?
I was just saying maybe you can move on and show us something else.
Yes, yes. I'll go now to the other side so that you can see the mu spectrometer.
Yeah.
What you saw, this part of Alice, this is the central part, which has this cylindrical form. Behind it, there is a sort of separate part, the mu spectrometer, which, as you will see, has a different form. It has a big dipole magnet and then detectors in the form of slices, one after the other. This is what we call the forward geometry. So,
in fact, Alice is actually not symmetrical, not like
no, it's not, exactly.
Atlas and CMS. Atlas and CMS are symmetrical. Alice is not, right?
It's not. It has the central part and the mu spectrometer on one side. I guess if we had made a similar mu spectrometer on this side where I am now, this would be more or less symmetric, but here that would mean higher cost. But also, as you see here on this side, there is a big frame. We call it mini frame, but it's not so small. It supports all these cables that go in, and also the pipes with the cooling liquid. So I'm now walking in a corridor along Alice to go to the other side. You see all these cables going in. You can see again this red stuff is these huge doors here. If you see here these tubes, these are for the water that goes to the other side to cool the dipole of the mu spectrometer. How much water is used? I don't know. I'm sorry.
Actually, Despina, you're just coming to your emergency exit on the right-hand side. It's a strange emergency exit, isn't it? Because
yes, well,
you're only allowed to use this under strict conditions. But actually, if you go through that door, you actually come to the LHC bypass tunnel, don't you? And you can get into the LHC through that door. But we can't go through that today, unfortunately.
No, only in case of emergency. As this sign indicates, we have the right to break it and go there.
Yeah.
Otherwise, we only have access here in our cavern. So what you see here is the muon spectrometer. What you see behind this scaffolding is the dipole magnet. You see the iron, blue. On it, you see the tube for the cooling. And hopefully you can see behind the scaffolding one of the poles of the magnet. And then there are panels supporting the muon chambers. There are 10 stations with muon chambers in total. You see 4 panels here. There are another 6 stations inside the magnet, so you can't see them. Then this cylinder, sort of cylinder that you see between the panels, this is the beam pipe, which has a diameter, the beam pipe itself, of some centimeters. And in this region, in this the area of the muon spectrometer, it is surrounded by a lot of absorbers in order to absorb the other types of particles and let through only the muons. Actually, inside the solenoid, there is also an absorber. Okay, you can't see it now. You just see the back doors which are closed permanently. And there is another final filter, this blue iron wall, which is 1 meter thick. And it is there to cut particles that maybe had managed to reach that point and let through only muons. So the detectors after this iron wall in the other panel, these detectors are the trigger detectors for the muon system. In general, in each experiment, trigger is the system that decides if the information is interesting in order to record it or not, in which case we throw it away. Well, we don't record it. And this is to decide if something is a muon.
Despina.
Yes.
Are muons passing through you right now?
Sorry?
Are muons passing through you right now?
Sure. Because muons from cosmic rays. I don't know if people are familiar. Muons are particles like electrons, which are what we have in atoms. They are particles of the same family, of the same category, leptons, but they are 200 times heavier. Here, the muon spectrometer is placed at the end of Alice because muons do not interact very much. They interact with matter and ionize it, but they do not interact in the same way as electrons, which produce what is called breaking radiation, Bremsstrahlung, and eventually stop. And here we're talking of high energy muons, so they go through everything else and come here. In the same way, muons from cosmic rays, which are actually secondary products of cosmic rays, reach all the way to where I am, the most energetic one, of course, because they manage to go through all the material which is on top of me. And
through the Earth.
And
through
we actually sorry.
Through 50 meters of Earth, actually, yes. And they
yes.
do that at CMS, and they do that at Atlas as well. Some people ask, we haven't asked about this when we've been to CMS. Do they cause a problem? Do they interfere with the experiment? Because you're having muons produced in your collisions, but your detector is also seeing muons which are coming from outer space.
Not really, because the direction is completely different. Here, with all the detectors that we have, we can define the point of origin of all particles. And actually, when we take data, the trigger is based on anyway, it's synchronized so that we see the collisions, but also we see the direction. Muons from cosmic rays they have a completely different direction, so they can't be confused. But actually, since we're talking about muons, cosmic muons are very useful because we use them when there is no beam in the machine, in order to commission our detectors, meaning to make sure they work, to calibrate them, to check the alignment and so on. So as soon as we are ready, I don't know in how many months time, we will start taking cosmic runs. We'll take data with cosmic exactly in order to make sure that everything works. And actually in this way, we also do some studies of cosmic rays on the side, let's say.
Okay, so Alex has just left us, but thanks for being with us, Alex. He's gone. Okay.
So maybe I go now to the, if there are questions, I can answer while I'm watching. I think I'll now go to the, near the beam pipe.
Let's have a look at the chat. Let's see. So how much, what does it feel like to interact with and build witness Alice in operation? This question is for anyone who wants to answer. Well, we have somebody here who helped build part of Alice. What's it like to know that the work that you did, how many years ago was it, Michael, is the key?
Yeah,
I mean, key to the running of the Alice experiment. How many years ago did you start building the TPC?
I've just found pictures when the spinner comes up. I will show some pictures from 2004 when the Alice TPC field gauge was about to be finished from the construction. So it's quite a long time ago.
When did you start? When did they start designing it?
Well, the design of the field gauge started 98. But the design that Alice has wants to have a field gauge and the TPC was much earlier from the design of the Alice experiment. So you have the Alice design, the general design. To start this, you need to have a studies what you want to study and how you want to measure it and how you want to study it. And then, of course, you have each subdetector has to do special studies for the details what they have to of the performance. Just one point to the to our audience, in case you want to see the picture of Despina and not me, you have to go to the participants list and pin the camera of Alice at LHC point 2, because then you will always see Despina's picture of the video, please. Otherwise, you would see the black image. If Mick is talking and if I talk, you see me. But if you want, of course, the interesting picture right now is what Despina is showing.
So I'm now going near the beam pipe. Sorry, yeah.
So this is a super exciting view what Despina shows us now, because there you see a colleague who is really right at the center where the collisions will take place. This is a place you cannot access at Alice or at CMS or Atlas, because they are a little bit differently reconstructed. But here you really see the heart of an LHC experiment and how our colleagues are manipulating the installation of the very closest detector.
So I guess these people are.
Is the thing in the center? Is that the beam pipe?
This is the beam pipe, and you see that it stops at some point. And then I will show you on the other side the beam pipe that comes, well, that goes inside the wall and then to the tunnel. Exactly where I am, the piece is missing, but eventually it will have to be installed, because before putting beam in the machine, it's necessary to make very high vacuum. Otherwise, the collisions of the beams with the air would destroy the beam. So you see.
Can you go back once more, Despina? Can you go once more close back to the where our colleagues are
Yeah, I'll go to the other side. Sure.
Great, thanks.
Remember, pressure 10 times lower than on the moon inside that tube. Pressure 10 times lower than on the moon.
Okay, here you see engineers and physicists. Well, I guess they are checking the ITS, the inner tracking system.
Notice that they have another handicap actually in these days. You always had to wear a helmet, you always had to wear safety shoes, but today they got to do all this work wearing a mask as well.
Yeah.
Tough job.
So, you see now I'm in the inside of this mini frame, and you see all the cables that it supports. Let me see. Okay, maybe when I go down, I was looking for a place where you can see the optical fibers, because the signals are transformed to optical signals. They go up to the computers with optical fibers, and then they are transformed again to digital information which is recorded.
And of course, all the data ends up at the CERN Computer Center, which we passed on the first bike tour on the way to the antimatter factory.
Okay. So I think these are the optical fibers that transform the signal and then send it upstairs. So I'll start slowly coming up. Here you see you see force cooling plant. Force is one of the detectors, photon spectrometer, that detects photons. It has some thousands of crystals, similar to what CMS has. I don't know if you have seen already CMS. And we cool them at -20 degrees in order to increase their light output.
So once again, Despina, we're seeing that CERN is not a particle physics laboratory at all. It's actually a heavy engineering laboratory.
Well, maybe while we are, while Despina comes up.
Actually, we're nearly been going for an hour, Michael, so we can
I'd like to
accept questions or show some photographs, but people can also feel free to leave.
Yes, you see my I want to show you some pictures of the ALICE TPC field cage 2004. So this is a portrait of mine.
Is that you?
It is me.
When you were young.
Yes. Thank you, Despina.
When he was younger.
So it's me making a picture of the central membrane, and there you see me, and this is, of course, I take a picture from below, and this central membrane is a stretched aluminum foil, so it's a perfect mirror. So and there you see the structure of the strips. And if I go to the next, so how can I get to the next picture here? Wait, let me see. Well, maybe this one. Yes, this is another.
Wow, I
this is
remember
another-
that.
Yes. So, and there is, I made a picture. This is like a big kaleidoscope, as you can see. It's yellow because we painted the floor where you have to walk around to install. We painted yellow. That's why you have the yellow reflection. But of course, you have the aluminum strips, and there I made pictures of Mick, where you could see him 10 times.
Yeah,
So-
it's probably 9 times too many, but never mind. No,
And
but I
there's-
remember that was an amazing experience too. You can imagine standing inside there,
Yeah.
wearing white overalls. Actually,
So
you had to keep the whole thing clean, very clean.
another view of a little bit artistic view. So it's pretty very beautiful and nice, and beautiful object, but also not beautiful, just beautiful, but also very precise and well technological detector.
Michael, if you went in there today, would it still look like this, or would it have deteriorated over
Well,
time?
no. It would not. The field cage is definitely the same. Otherwise, it would not work anymore. But they are changing just the readout chambers. So the type of the readout chambers on both sides is changing technology. It will still be a gases detector, so using gas as a tracking device. But the how you translate the electrons kicked out by the particles and then measured, how they are measured, it's they use a different technology in the next round.
But visually, would it look so as clean and as shiny?
Yes, absolutely, because there we also had masks during installation. Okay, so I would say now, let's see.
Well, has anybody got any questions they want to type into the chat? If not, we can think about stopping, but I think we have to say, wait for Despina and say a big thank you to Despina.
I'm here. I'm in
She's
the
here.
control room.
You are? I didn't know where you
Yeah.
are. Okay,
Yeah.
okay.
Voila.
Despina is from Greece, by the way, if you were wondering where she might come from. And she's a great swimmer. I mean, the last time that I saw Despina was in the local swimming pool, not very far from the CERN main site, a few days ago.
So well, I have to switch on here because now
We are back. You may switch off.
Many cameras.
Yes. No, I just want to say goodbye, to thank you for your.
Okay, I say goodbye from here and disconnect from this telephone. So thanks a lot for the attention to everybody. Bye bye.
Thank you, Despina. Despina takes many people from all over the world to see the ALICE experiment. So she's a very experienced CERN guide. And that she does in her spare time.
okay. So then
Hi, everybody. I am
Hi.
driving. So I
Again,
have to...
again, you're always driving at this time of the day.
No, it's terrible.
okay, good. Then I would say
I missed it.
I will stop recording now.
Okay.
And